So welcome to our demonstration video on UMAP um, on our course ST9 exploratory data analysis. So UMAP is a more common nonlinear dimensionality reduction technique. It's like TLC in terms it tries to reduce many features into more simple a 2D plot containing the main components. So it tries to force many components onto the single plot. But it tries to balance the local and global structure. So to an extent, the local and global distances have a qualitative meaning, but it's not strictly quantitative. So it's very good on large data sets. Um, it is stochastic, so consider using a seed, and we need to consider the number of nearest neighbors and minimum distances as well. So this is very good for flow cytometry data, a single cell sequencing data, and other similar data sets. So we need to consider the number of neighbors, how many nearest neighbors point each considers in terms of clustering. So we have a small number, we may be looking at the very local structures only, whereas if we have a large one, we will be considering the broader picture for that particular parameter. Value 15 is a good starting point for data sets of 100 to 1,000 samples. We also have the minimum distance, which is how tightly points are packed together in two-dimensional space. We might start off with the default one to see how well they work. We might have small values which are less than 0.1 and large values that are more than 0.5. And these are better for looking at gradients than large values, whereas the other ones are looking better for looking at tight clusters. So what we can do is try multiple options and see how they work. And our rationale behind this is the same as previously. We have four options we're going to go through for the neighbor values, 7, 15, 27, and 40. I'm going to create a 2 by 2 plot in the same way as before for these options. We can't find the function UMAP, so our way of solving this is the same as before. We just search for it in help. And what we can see is we view what UMAP as being our library that contains that one. So let's loop through that again and try to spell it properly with help. And you can see it takes some time to complete this command. And so we can compare these four plots when they appear. So you can see there, as we increase the number of neighbors, there's no fundamental change here in terms of the clustering that we see. Um, the, the structure remains the same. And we can apply the same thing for our distances. We can add in the package name we're using and apply this in the same way and see if those minimum distances make any difference. So you can see the first one, there's no clustering. The second one, there's no real differences. And same for the final two. So it appears to have no substantial differences here. And what we can do as well is use our default value of just a minimum difference of 0.1 and nearest neighbor of 5 and take this as the one that we will look at. So what we can do is take our coordinates for those two ones and view them to see we can see the first chunk of where the samples lie on this new coordinate system. And then we can plot that in the same way that we had before using ellipses. So you can see the separation of UMAP here is maybe not as effective as the other approaches. And we see that they're quite mixed together and it's maybe not the most helpful. So if this hopefully kind of illustrates, if you look across the different plots that we have across MDS, PCA, TSNE, and UMAP, how you can get different outputs and they have different levels of information, types of information that you can obtain from them. And if you're trying to make inferences about your data set, you have to think carefully about what approach you're using.